Welcome to our MAE 152 design project for the Formula SAE race car. Here is a table summarizing the parts that we analyzed. For the chassis, the first design iteration included a reinforced side and rear, and the second design iteration included front crossbars and reinforced rear corners. For the first static analysis, the front impact showed improved results for both iterations with a best at 83.84 megapascals. Next, the rear impact showed the best result of 220.41 megapascals. And finally, for the side impact, same force, the best result was 1,067 megapascals. The next static analysis was a vertical bending from the load of the driver sitting in a car. The design did not improve this at all, and the best was 150.72 megapascals. For the torsional stiffness, the second design iteration yielded best results at 142.56 megapascals. For the frequency analysis, the engine's frequency does not come close to interfering with any of the chassis' natural frequencies.
And here is the wishbone design with the first design iteration of shortening the outer arms and the second design iteration thickening all three bars instead. And the first analysis ran with a static analysis to simulate a sort of bump impact. And as seen by the results, even though the first iteration significantly improved the total stress applied, it still failed under all three conditions. And here is the tensile analysis ran instead, where the first iteration once again improved the design over the original design. And while the second iteration also did not yield, it still did a bit worse than the original design. And here are the results for the modal analysis. And since the frequencies are quite high, there should not be any interference with the frequency of the engine. And here are the closed form solutions for the wishbone, and the displacement results are quite similar to the results that were found in the simulation, although the stress results are quite off as seen earlier.
One important part of the suspension assembly is the push rod. It takes the brunt of any upward forces from bumps in addition to the weight of the car. And as a result, it's subject to a high compressive force. So I performed a static compression analysis on the push rod through 2 design iterations, where I thickened the center shaft's diameter by 5 millimeters. As you can see, the stress did not change much, but the displacement did decrease. So up next, I also did a modal analysis because this part will be exposed to imperfections in the road, which will lead to vibrations under load. And so I ran the modal analysis at the 3 different design iterations, and here's the data for that. As you can see, it had quite a significant impact in the frequencies.
For the rocker, the original design is overkill in some areas, and in other areas, there are high stresses. So the first design iteration is to add fillet to the high stress areas and also cut out the center where there's barely any stress. The first impact analysis is when the suspension is fully extended, and the best iteration is the first iteration with a stress of 2.4 megapascals. For the impact analysis, on when the suspension is fully compressed, with the second iteration, the weight is reduced by around 80%, but the maximum stress is still a lot lower than the yield strength of the material. The third analysis for the rocker is the impact analysis for when the suspension is rebounding. That creates tension inside the rocker arm. And with this, even for the second iteration, the maximum stress is only slightly higher than the original design maximum stress at 2.7 megapascals. For the frequency analysis, even the lowest frequency is over 100 hertz, which is way above any frequencies that a race car would experience when racing.
There's an SN curve for 4130 steel. It is a commonly used steel for Formula SAE, high strength and lightweight. Most of our parts will experience around 10,000 cycles with relatively low stress. Product life is not a big concern, even for the aluminum parts.